So here's the second part of the solutions video just for question 3. So while on nightly walks with her dog, Kelly noticed that the moon appeared to be at different angles on different days. She researched the maximum altitude of the moon in degrees and obtained this data starting April 1st. So we need to graph Kelly's data and estimate the period, explain why a sinusoidal function can be used to model the data, determine the equation of a sinusoidal regression function that models the data, find the maximum angle of the moon, estimate the altitude of the moon in degrees on day 100, and round to the nearest tenth of a degree, and find the first day in May that the altitude of the moon will drop below 30. So there are a few steps involved here. So for this, let's go to our TI Connect software. So we're going to start by entering in all of this data. So I've got 30 data points entered here. And now we're going to calc. And again, go to option C, sinusoidal regression. Here we have to estimate our period. And our period here seems to fluctuate a little bit. It appears to be about 28 days, which is consistent with what we'd expect just from our understanding of astronomy. So, all right, and then we are going to calculate. And we do get a fit. So question A, we have to graph Kelly's data estimating the period, which we have done. So that initial guess of the period has been adjusted to a better fit. So we'll graph this. Again, plot, do our zoom stat, and graph it this way. So now we have our graph. So explain why a sinusoidal function can be used to model the data. A sinusoidal function can be used to model any periodic data. And because the moon has a period, right, it has a regular repeating pattern, a sinusoidal model can be used to fit it. The equation of the sinusoidal model is the one that we got back here from our regression, which answers part C. Part D, the maximum angle of the moon, will be our A plus D. So that will be roughly 63 degrees. So we want to estimate the altitude of the moon in degrees on day 100, round to the nearest 10th degree, and find the first day in May that the altitude will drop below 30. So for this, it might be easiest to flip back to our Desmos graphs. And we are going to start by entering in what we got for our sinusoidal function here. So when we do that calculation, we got that A is 22.954144123. Our B value is 0.23034118828. Now the C value that we see on display in the calculator is in that bx plus C form, not the b times x minus C form. So that's 0.208486178 is what the calculator shows us. We need to divide that by negative b to get our actual phase shift. And our D is 40.28414.233. These data points were from a previous question. We no longer need them. And it looks like we've killed the graph. But what we're really shooting for is to now adjust our X and Y. So we know our maximum is going to be about 63. Let's make our Y max 65. We're now seeing some data here. Our minimum gets down as low as the 20. To be sure, let's go with the full x-axis. We're going to go from day 0 to day, say, 110, since we're looking for day 100. And now our minimum comes in at 17.33, so let's set our y minimum at 15. This will have the graph. So we want to find the altitude on day 100. X equal 100. Bingo, it's going to be about 23 degrees. They asked for the nearest tenth of a degree, so that makes it 23.3. And the first day in May that the altitude of the moon will drop below 30. We're starting April 1st. So May starts on day 31. That is May 1st. And we want it below 30 degrees. So there we go. We are at that 44-day mark. So 44 days in is going to be the first day it drops below. 44 minus the 30 days in April gives us May 14th. So May 14th is the first day it drops below that level. And this finishes assignment 3.08, number 1.